All right, here we go. So in this video, we're going to learn a little bit more about systems of objects. And these problems, when you first see them, they're going to look really familiar. There's an important distinction. All right, so we've done systems of objects in the past, but when we've done systems before, all of the objects have just been moving linearly, and we've not had any parts with any sort of rotational motion. All right, this time we're going to have systems that have either a couple things that are rotating, or more often than not, we'll have an object or two that are moving, and probably one object that's rotating. All right, and so you're still going to treat the objects that are not rotating, just the objects that are moving linearly, the same way we always do, by using net force equals net force. All right, but there becomes an extra bit of complication if you've got an object in the system that's rotating. You've got to use net torque equals net torque, and what connects everything is the fact that we can always write an expression that connects the angular acceleration of the rotating thing equal to the linear acceleration of the non-rotating thing by using one of our jumper equations, okay? So that's kind of the deal there, all right? So probably the easiest way to do this is to just do an example, all right? So we've done problems like this before. So here we've got, this 6 kilogram block over here sitting on an inclined plane, which is inclined despite the crappy drawing, it's inclined at an angle of 30 degrees, okay? And then we've got this, this 2 kilogram object over here, and it's going to move, right? And so in the past, what we would do is we would either sort of consider the 2-block system and understand that the whole system is going to slide this way and kind of deal with it that way, right? So that was sort of the honors approach. And then in AP, what we've been doing is we've been kind of doing a net force equals net force thing, right? So if we did that, what we can do is we could make 2 free body diagrams, right? We'd go, all right, so here's this 2 kilogram thing, right? And so let's see, what force is that on it? Well, there's a gravity force and there's a normal force, but we don't really care about those because they're going to cancel out. And then you've got this tension force pulling the system forward, right? And then we could write a net force equals net force equation in which we would say that the tension is equal to the mass times the acceleration, right? Okay, and then we could repeat the same process over here for the red block. And we go, all right, we've got this red block. And let's see, gravity, we got to split it up into components, don't we? All right, so let's see. So if we split gravity up into components, what you discover is that your FG parallel is 29.4 newtons. That's pulling it down the hill. And then there's an FG perpendicular and a normal force, but those two guys cancel out, so we don't really care about those. And then there's a tension force, right? Okay, so this all looks like what we've done before, and then we could write a net force equals net force equation. Let me free up a little space here, since I have not done a great job managing. Let's do one of these. All right, so that's that, and then over here, whoa, that's not at all what I wanted to happen. Let's try that again. These guys, over here. All right, and then we can write a net force equals net force equation, which is going to be what? Our force of gravity parallel, 29.4, minus our tension equals mass times acceleration, right? Okay, so at this point, what we would do is we'd say, oh, cool, I got 2 equations and 2 unknowns, right? I've got tension and acceleration, and I've got tension and acceleration, all right? And that's how we would have solved that before. Now, when we did that before, what I haven't addressed yet is that in the past, we've always assumed that our pulley here was frictionless and massless, which meant that it didn't take any torque to make it turn, okay? And so what that meant then was that since we didn't sort of need any torque to make this pulley turn, it meant that you sort of didn't lose any of the force provided by your tension turning the pulley, and so that meant that this tension force and this tension force were equal. Okay? Now, unfortunately, in the real world, pulleys have mass, and therefore they have rotational inertia. Okay? And so the idea is, in this problem, our system is going to move this way, which means our pulley needs to turn this way, which means the tension pulling this way has got to be bigger than the tension pulling this way. So our two tension forces are not, in fact, equal anymore. All right? In other words, there's a, how do I want to say this? Let's see. So, the tension in this whole chunk of the rope is uniform. So the tension pulling the pulley this way is the same as the tension pulling the 2 kilogram block this way. Okay? But that can't equal the tension in this chunk of the rope, right? Because this tension here has to be bigger than the green tension, otherwise the wheel wouldn't spin, right? So we've now got two different tensions, all right? So we got to number the two chunks of our rope, all right? So let's call the chunk, let me see how I did it in my notes so that I don't get things mixed up. All right, so let's call this chunk 1 of our rope, and let's call this chunk 2 of our rope. All right, and so now we've got two different tension forces, right? There's tension number 1 pulling the 2 kilogram block, and there's tension number 2 pulling the 6 kilogram block, all right? So now we've got three unknowns, right? We've got one unknown acceleration and two unknown tension forces, right? So we need a third equation. Where does that third equation come from? Oh, from our third moving object. All right, so here's my wheel, right? And here's what we know. Tension number 1 is pulling it that way. Tension number 2 is pulling it that way. And so now I can write a net torque equals net torque equation for that. So net torque equals net torque. So that's the torque of tension number 1. So I did kind of a weird thing here. I'm going to assume, I guess it doesn't really matter. So in my head, I was thinking that this direction, the acceleration would be positive, which would mean the wheel spinning this way would be positive, which is actually clockwise. So if that's going to weird you out, then you got to make your acceleration negative to make your torque also end up being negative. Long story short, I'm going to make this direction positive and this direction negative. All right. Again, just like in honors, you know, the directions of the signs are somewhat arbitrary. All right. So up until this point, I've always used clockwise as negative. I'm changing that here for this problem so that everything kind of matches up. All right. So the only negative I'm going to have here is the torque from tension number 1. So I'm going to have negative force of tension number 1 times the radius, which we know is 0.25. So I'm going to put that in. You know what? I'm just going to put R. All right. And then, all right, sorry, kids, my kids are all playing laser tag. Anyway, sorry. So I know I gave you the radius here. I don't think we need it. I solved it using it. I'm going to leave it out for a minute. We'll plug it in a minute. So here's our radius. We'll just call that R. Okay. So that means the torque produced by tension number 1 is whatever the force of tension 1 is times the radius, plus the torque from tension 2. So that's force of tension 2 times radius. So that's my total torque, equals net torque, which is I times alpha. Well, let's see, this thing is a disk, and I for a disk is 1/2 mr squared, right? So I guess I should use the lowercase r, right? So 1/2 mr squared. So this is I, 1/2 the mass, which I'm going to actually plug in, times r squared, times alpha. I was right. It doesn't matter. So the idea is the linear acceleration of a point on the outside edge of the wheel is equal to the angular acceleration. The angular acceleration is equal to the linear acceleration of a point on the outside edge of the wheel divided by the radius. So here's my I, and then my alpha is just A over R. Okay, and so R squared over R, those guys cancel, and then all of my R's here cancel. So yes, the R's there do not matter. And so after you simplify this, you end up getting force of tension 2 minus force of tension 1 equals 1/2 of 16 is 8 times A. So I've now got 3 equations and 3 unknowns. These are, oh no, my 3 equations. And so now we can solve this mess. So how you do this is totally up to you. At this point, it's just kind of grind through the algebra. So I think what I would probably do is I would solve the blue and the red equations for the two tension forces and plug those in. So the blue one's already solved for tension. Let's solve the red one for tension 2. And you got force of tension 2 equals, what, 29.4 minus 6A. So now I'm going to substitute this in here, and I'm going to substitute this in here to give me, oh, here, we'll do this. We'll embiggen our screen. Oops, maybe. Come on, smartboard. There we go. All right, so force of tension 2, that's, 29.4 minus 6A minus force of tension 2 is 2A equals 8A. So this is minus 8A. So if I add 8A to both sides, then I get 29.4 equals 16A. Divide both sides by 16, and you will discover that the acceleration of our system is 1.8375 meters per second squared. And then once you've got that acceleration, you can plug it back up in here to find tension 2, or I guess plug it in here to find tension 2, and plug it in over here to find tension number 1. Okay? Long story short, to solve these problems that deal with systems of object, your best bet is system of equations. Each object gives you an equation, okay? And the idea is, in this problem, we had 3 moving objects, and that resulted in 3 equations, 1 for each object. All right? So that's how you do those, and it's just kind of getting used to them. The real big trick, like I said, is this, that you can replace your angular acceleration with A over R, okay? And then usually all of your R's will cancel, all right? So there you go. I'm gonna shut up now and take my kids home because I think they're tired of playing laser tag in the hallway.